You've heard it 1,000 times. Everything is made of energy. Stars are energy. Atoms are energy. You are energy. It sounds profound. It sounds like science. But here's the problem. When physicists actually sit down and describe what energy is in quantum physics, they don't describe a substance at all. Energy isn't a glowing fluid hidden inside atoms. It isn't a building block you can hold or split apart or look at under a microscope. In fact, the moment you try to treat energy as a material ingredient, as some kind of cosmic stuff that objects are made from, the physics falls apart. So, if energy isn't a thing, if it isn't made of smaller pieces, then what exactly is it? Tonight, we're going to answer that question properly. And the real answer is stranger, more elegant, and more unsettling than almost anyone expects. Before we dive in, if you find these kinds of deep explorations interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let me start with something you already think you understand: energy. You use this word constantly, every single day, without really thinking about what it means. You buy energy drinks, you pay energy bills, you eat breakfast because your body needs energy to get through the morning. Your phone dies because it runs out of energy. A car needs gasoline because it needs energy to move. You need energy. The entire global economy is organized around producing, distributing, and consuming energy. It seems like one of the most straightforward, most intuitive concepts in the world. And underneath all that everyday familiarity sits an assumption most people never question. The assumption that energy is a thing, a substance, some kind of invisible material that gets stored inside objects and then released when those objects do something. Your food contains energy. Your battery stores energy. Gasoline is packed with energy. The sun radiates energy. When you hear phrases like this from childhood onward, you naturally start picturing energy as stuff, an invisible, glowing essence living inside matter, something real and tangible, just too small or too subtle to see directly with your eyes. This picture feels perfectly natural. It feels like common sense. But here's the problem. It's wrong. Not slightly wrong, not approximately wrong in a way that doesn't really matter. Fundamentally, deeply, structurally wrong. And understanding why it's wrong is the essential first step toward understanding what energy actually is, according to physics. Because the history of science is filled with moments where humanity's most confident, most intuitive picture of reality turned out to be completely mistaken. We thought the Earth was flat. We thought the sun orbited the Earth. We thought diseases were caused by bad air. In every case, our intuition felt perfectly reasonable. In every case, it was wrong. And the story of energy follows this same pattern in a way that most people never learn about. To understand why, we need to go back a few centuries, because this exact confusion, this specific mistake of treating a measurable property as though it were a physical substance, has happened before in the history of science. And the story of how scientists corrected that mistake is one of the most revealing episodes in all of physics. It's a story about heat. In the 1700s, one of the biggest open questions in natural philosophy was deceptively simple. What is heat? When you put a pot of water over a fire, the water gets hot. Something seems to flow from the fire into the water. When you place a hot iron next to a cold stone, the iron cools down and the stone warms up. Something seems to transfer between them. The question was straightforward. What is that something? The most widely accepted answer was caloric theory. Caloric was imagined as an invisible, weightless, self-repelling fluid that permeated all matter. Hot objects contained a large amount of caloric, Cold objects contain less. Heat transfer was simply caloric flowing from regions of high concentration to regions of low concentration, like water flowing downhill from a full basin to an empty one. Antoine Lavoisier, one of the greatest chemists who ever lived, was a prominent supporter of this idea. In 1789, he included caloric on his table of chemical elements, alongside oxygen, hydrogen, and nitrogen. To Lavoisier and many other scientists of his era, heat was genuinely a material substance. You could almost imagine scooping it up and pouring it from one container to another. It was conserved. It flowed in predictable directions. It behaved, in every obvious way, like a real physical thing. And the remarkable thing about caloric theory is that it worked. It worked really well for a wide range of everyday observations. It correctly predicted that heat flows spontaneously from hot objects to cold ones, never the reverse. It explained why objects expand when heated, because the caloric fluid taking up space inside them was increasing in volume, pushing the material apart. It even provided useful insights into how steam engines operated. Sadi Carnot, a brilliant French engineer, used caloric theory in 1824 to analyze the maximum possible efficiency of heat engines. His analysis was groundbreaking, and some of his results were actually correct, even though the underlying model he was using was completely wrong about what heat fundamentally was. This is an important lesson, and it applies directly to our question about energy. A theory can make useful, accurate predictions while being fundamentally mistaken about the nature of the thing it describes. Caloric theory described the behavior of heat quite well in many situations. It made good predictions. It was useful for engineering. But it described the nature of heat incorrectly. Heat was not a fluid. Heat was not a substance at all. And the first major crack in caloric theory came not from a university lecture hall, but from a cannon factory in Munich. In 1798, a man named Benjamin Thompson, also known as Count Rumford, was supervising the boring of brass cannons. Boring is the process of drilling out the interior of a cannon barrel using a large, rotating metal tool pressed against the brass. It's a brutal, grinding operation, and it produces enormous amounts of heat. The brass shavings that came off during boring were extremely hot. Under caloric theory, this was easy to explain. When you cut metal into smaller pieces, each piece has less volume and therefore can hold less caloric fluid. The excess caloric escapes as heat, warming the shavings, simple and clean. But Rumford noticed something that caloric theory could not explain. The heat never stopped. As long as the boring tool kept grinding against the brass, heat continued pouring out without any sign of diminishing. He could dull the boring tool completely, so it was no longer cutting the metal at all, just rubbing against it uselessly, and the heat kept coming. Rumford set up a dramatic demonstration. He immersed the cannon barrel apparatus in a box filled with roughly 18 pounds of cold water and kept the dull boring tool turning against the brass for about 2.5 hours. The water started cold. It warmed. It grew hot to the touch, and then it began to boil. 212 degrees Fahrenheit. The water boiled purely from the heat generated by metal grinding against metal. No fire, no flame, no chemical reaction, just friction. This was devastating for caloric theory. If heat were a fluid stored inside the brass, it should eventually run out. You can only squeeze so much water from a sponge. There is a finite amount. But Rumford's experiment showed no sign of the heat supply running out. The heat production appeared limitless, constrained only by how long you were willing to keep the boring tool turning and how much effort you were willing to supply. As long as mechanical work was being done, as long as the tool kept grinding, heat kept appearing without any decrease in intensity. Rumford concluded that heat could not possibly be a material substance. There was no caloric fluid hiding inside the brass waiting to be released. Instead, Heat was being generated by the mechanical motion of the boring tool. Heat was somehow a product of motion itself, not a transfer of stored fluid. He wrote that anything which any insulated body or system of bodies can continue to furnish without limitation cannot possibly be a material substance. The supply was inexhaustible. Therefore, heat was not a substance. It was something else entirely. This was a radical conclusion. Most of the scientific establishment was not immediately convinced. Caloric theory had been taught in universities across Europe for decades. It had prestigious supporters and a long track record of useful predictions. People had built their careers on caloric theory. And while Rumford's demonstration was dramatic and deeply suggestive, it lacked the precise quantitative measurements needed to establish a definitive alternative. He showed that unlimited heat could be generated from motion, but he did not determine the exact mathematical relationship between mechanical work and the heat produced. How much work creates how much heat? What is the conversion ratio? Those crucial numbers were missing, and establishing them required someone with a different kind of obsession. About 45 years after Rumford's Callan experiment, an English brewer named James Prescott Joule began a series of meticulous experiments that would settle the question for good. Joule was obsessed with precision. He wanted to know exactly how much mechanical work was needed to produce a specific amount of heat. Not roughly, not approximately, exactly. His most famous apparatus was elegantly simple. A falling weight was connected by a string and pulley system to a paddle wheel submerged in a carefully insulated container of water. As the weight descended under gravity, it turned the paddle wheel. The paddle wheel churned the water, creating friction between the paddle blades and the surrounding liquid, and the water's temperature rose. By precisely measuring the distance the weight fell, the mass of the weight, the mass of the water, and the tiny temperature increase, Joule could calculate how much mechanical energy was required to produce each unit of heat. The experiments were painstaking. The temperature changes were small, sometimes only a fraction of a degree. Joule needed extraordinarily sensitive thermometers and exceptional patience. He repeated his experiments dozens of times, under different conditions, using different methods of generating heat. He used paddle wheels in water. He used paddle wheels in mercury. He used the friction of iron plates rubbing together. He compressed gas and measured how it heated up. He ran electrical currents through wires submerged in water. And in every single case, no matter how the heat was generated, the answer came out the same. A specific amount of mechanical work always produced the same amount of heat. The conversion ratio was constant. It did not matter how the work was performed. Whether through friction, compression, electrical resistance, or any other process, the ratio was always approximately 4.18 joules of mechanical work for every calorie of heat. This number, called the mechanical equivalent of heat, was universal. It didn't depend on the materials involved, on the method of conversion, or on the conditions of the experiment. It was a fixed fact of nature. This result accomplished something far more important than just disproving caloric theory. It established a fundamental connection. Heat and mechanical work were interchangeable. They were different forms of the same underlying quantity, a quantity we now call energy. You could convert the organized motion of a falling weight into the disorganized molecular jiggling we call heat, and the conversion always followed the same fixed ratio. Energy was not being created or destroyed in these transformations. It was changing form. The recognition that heat is molecular motion, not a substance, was the final nail in caloric's coffin. When you rub your hands together and feel warmth, you are not releasing some hidden fluid from your skin. You are converting the organized, large-scale motion of your hands into the disorganized, tiny-scale jiggling of trillions of molecules in your skin. Those vibrating molecules are what we detect as heat. When a fire heats water, the fast-moving molecules in the flame transfer kinetic energy to the slower molecules of water through collisions, making them move faster. That faster molecular jiggling is what a thermometer registers as higher temperature. Heat is motion. Not a substance, not a fluid. Not a thing you can hold, pour, or store in a container. Motion. Now here is why this history matters for our question about energy. The caloric story reveals a pattern we need to recognize because we are caught in the same trap right now. Scientists had an observable phenomenon: heat. They created a mental model for it, an invisible fluid called caloric. The model was useful, it made good predictions, but it was fundamentally wrong about what heat actually was. Heat was never a substance, it was always a property, a description of how molecules are moving. And if you look at how most people talk about energy today, you see the exact same pattern. You say a battery stores energy. You say food contains energy. You say the sun produces energy. You say energy flows through a wire. Every one of these phrases treats energy as though it were a substance, a fluid, a material that gets contained and transported and released. It sounds exactly like caloric theory. Replace the word energy with caloric fluid in those sentences, and you would have the same conceptual picture that scientists held about heat in the 1700s. A picture that turned out to be completely wrong. So here is the question we have to face. If heat turned out to be a property of molecular motion rather than a substance, could energy itself be something similar? Could energy be a property rather than a thing? The answer, according to physics, is yes. That is exactly what energy is. Energy is a measurable property of physical systems. It is a number you can calculate, a quantity you can assign to any physical system based on its state, its motion, its configuration, its composition. But it is not a material ingredient. It is not made of anything. You cannot isolate a sample of pure energy. You cannot put energy in a jar by itself, separate from all matter and all fields and all physical systems. Energy always belongs to something. It is always a property of some physical system, never a free-floating substance drifting through the void on its own. Let me make this concrete, because abstract definitions only go so far. Consider a baseball flying through the air at 35 meters per second. We say it has kinetic energy. Kinetic energy is the energy of motion. We can calculate it precisely. It equals 1/2 times the ball's mass times the square of its velocity. For a baseball weighing about 145 grams, moving at 35 meters per second, that works out to roughly 89 joules of kinetic energy. But what is that 89 joules made of? Nothing. It is not made of anything. It is a number describing how the ball is moving. The ball is made of cork, rubber, yarn, and cowhide leather. Those are real physical substances composed of atoms. But the kinetic energy is not another substance hiding inside the ball alongside them. It is a description of the ball's state of motion. If a fielder catches the ball and it comes to rest, the kinetic energy drops to zero. It does not leak out. The ball does not get lighter. No substance escapes. The ball simply is not moving anymore, and the number describing its motion changes accordingly. Or consider gravitational potential energy. Lift a rock to the top of a cliff, and it has gravitational potential energy because of its position relative to the ground below. The higher you lift it, the more potential energy it possesses. Release it and it falls, and that potential energy converts into kinetic energy as the rock accelerates downward. But while the rock sits motionless on top of the cliff, is there some glowing substance packed inside it? Of course not. The potential energy is not inside the rock at all. It is a property of the relationship between the rock and the Earth's gravitational field. Move the rock higher and the number changes. The energy increases. But nothing material inside the rock changed. No substance was added or removed. A number describing the system's configuration shifted because the configuration itself shifted. Thermal energy works the same way. A pot of boiling water has more thermal energy than a pot of cold water. But the thermal energy is not some extra substance mixed in with the water molecules. Thermal energy is the collective kinetic energy of trillions upon trillions of water molecules bouncing, vibrating, and rotating. When you heat water, you are making its molecules move faster. The total kinetic energy of all those individual molecules increases, and we call that increase thermal energy. Cool the water down, and the molecules slow down. The thermal energy decreases. Nothing was added to the water or removed from it in a material sense. The molecules simply changed how fast they were moving. In every single case, energy is a description of what a system is doing, not a description of what a system contains as an extra ingredient. This distinction between a property and a substance might sound academic, but it is fundamental, and it is worth sitting with for a moment. Because our language constantly works against us. We say energy is produced, consumed, stored, released, transferred. All of those verbs imply a substance. You produce milk, you consume food, you store water, you release steam, you transfer money. These are all things we do with physical substances and objects. But when physicists use these words about energy, they mean something subtly different. They mean that a measurable property of one system decreases, while the same measurable property of another system increases by the same amount. When we say a battery stores energy, we mean that the chemical configuration of the battery's molecules is such that if you connect the battery to a circuit, the chemicals can rearrange themselves into a lower energy configuration, and the difference shows up as electrical current doing work on whatever the circuit powers. There is no tank of energy inside the battery. There is a set of chemicals whose potential energy is higher in one molecular arrangement than in another. Think of it this way. Color is a genuine, measurable property of surfaces. A red apple is detectably, measurably red. You can use instruments to determine the exact wavelengths of light it reflects. But redness is not a substance inside the apple, alongside the apple's flesh and seeds. You cannot extract the redness and put it in a bottle. You cannot weigh it. Redness is how the apple's surface interacts with light, determined by the molecular structure of the apple's skin. It is real, it is measurable, but it is a property, not a material. Energy works exactly the same way. It is real, it is measurable, it has consequences. A speeding truck has more kinetic energy than a parked truck, and that difference is very real if you are standing in its path. But that kinetic energy is not a substance flowing through the truck's engine block. It is a number calculated from the truck's mass and velocity. It describes what the truck is doing, not what the truck is made of. So if energy is a property, if it is just a number, why does it dominate all of physics? Why do scientists talk about energy constantly? Why do we build entire power plants and drill oil wells and cover rooftops with solar panels? If energy is not a thing, why does it matter so much? The answer is conservation. Energy is conserved. The total energy in any closed system, any system not exchanging energy with its surroundings, never changes. Energy can change form. Kinetic energy can become thermal energy when a moving car slams on its brakes and the brake pads heat up. Chemical energy can become kinetic energy when gasoline combusts in an engine cylinder. Gravitational potential energy can become kinetic energy when water falls over a dam and spins a turbine. Electrical energy can become light and heat when current flows through a filament. But in every single one of these transformations, the total amount of energy before the process equals the total amount after. Not approximately, exactly. This principle, the conservation of energy, is perhaps the single most important law in all of physics. And its discovery did not happen in a single flash of inspiration. It crystallized over several decades in the 1800s through the work of multiple scientists arriving at the same conclusion from entirely different directions. Julius Robert von Mayer, a German physician, proposed the idea in 1842, based on observations of how the human body converts chemical energy to heat at different rates in different climates. Joule established the principle through his painstaking laboratory experiments. Hermann von Helmholtz published a comprehensive mathematical formulation in 1847, bringing together mechanics, heat, electricity, magnetism, and even certain biological processes under a single unifying principle. Each of these scientists, working largely independently, recognized the same fundamental truth. Energy transforms. Energy converts from one form to another. But energy never appears from nothing, and it never vanishes into nothing. The books always balance. By the 1850s, the scientific community had broadly accepted what we now call the first law of thermodynamics. Energy is conserved in all physical processes. In over 170 years since then, no experiment has ever violated this law. Not once. Not even close. It is one of the most thoroughly tested, most consistently confirmed laws in the entire history of science. But accepting that energy is conserved still leaves a deeper question unanswered. Why? Why should nature obey such a rule? For decades after the law was firmly established, physicists treated conservation simply as an empirical fact. Every experiment confirmed it. Every process obeyed it. But nobody could explain why the universe should behave this way. What is it about the structure of reality that makes energy conservation necessary rather than merely coincidental? Is it just something we happen to observe, an accident of the particular universe we live in? Or does it follow from something even more fundamental? The answer, when it finally arrived, came not from a physicist, but from a mathematician. And it came from someone the scientific establishment had done its very best to ignore. In 1918, a German mathematician named Emmy Noether published a theorem that is now considered one of the most profound results in all of theoretical physics. Noether had spent years fighting against a system that refused to take her seriously because of her gender. At the University of Göttingen, one of the world's leading centers for mathematics and physics, she was not permitted to hold a paid academic position. Male faculty members objected to a woman lecturing to students. Her courses had to be officially listed under a male colleague's name. She was working for free, contributing fundamental results to mathematics and physics, while the institution around her denied her the title and salary that her work plainly deserved. Despite all of these barriers, she produced a theorem so powerful that Albert Einstein himself praised it as a piece of penetrating mathematical thinking. Noether's theorem states that every continuous symmetry of a physical system corresponds to a conserved quantity. That sentence is dense, so let me unpack it carefully, because this is one of the most important ideas in science. A symmetry, in physics, means that the laws governing a system don't change when you shift something. For example, the laws of physics don't depend on where you are. An experiment performed in London gives the same result as the same experiment performed in Tokyo or on the surface of Mars. The laws of physics are the same everywhere in space. This is called spatial translation symmetry. Noether's theorem proves mathematically that this symmetry, the fact that the laws of physics are the same at every location, is the direct reason momentum is conserved. Momentum conservation is not a coincidence. It is a mathematical consequence of spatial symmetry. There is also rotational symmetry. The laws of physics don't depend on which direction you are facing. An experiment gives the same result whether the apparatus points north, south, east, or west. Noether's theorem proves that this symmetry is the reason angular momentum is conserved. And here is the part that matters most for understanding energy. The laws of physics don't change over time. An experiment performed today gives the same result as the same experiment performed yesterday, or 100 years ago, or 1 billion years from now. The equations governing how objects move, how forces act, how particles interact, none of these have changed. This is called time translation symmetry. And Noether's theorem proves that this specific symmetry is the reason energy is conserved. Let that settle for a moment. Energy is not conserved because it is an indestructible substance. Energy is conserved because the laws of physics are constant in time. If the laws of physics were different tomorrow than they are today, if the equations governing forces and motion were shifting from one moment to the next, then energy would not be conserved. You could create or destroy energy freely. But the laws don't change. They are the same at every moment. And from that single fact, energy conservation follows automatically as a mathematical certainty. Noether proved it rigorously. The proof is airtight. There is no wiggle room. This completely transforms how we should think about energy. Energy conservation is not like the conservation of water in a sealed container. Water is conserved because water molecules are physical objects and they don't vanish. Energy conservation is entirely different. Energy is conserved because of an abstract mathematical symmetry in the structure of reality. The conservation arises from the rules, not from any substance being preserved. It is a feature of the universe's operating logic, not a feature of any physical fluid or material. And this is precisely why energy is so powerful as a concept. It tells you what transformations are possible and what transformations are forbidden. It tells you that if a system starts with a certain total energy, it will end with exactly the same total, even if every other detail of the system changes beyond recognition. A ball thrown into the air trades kinetic energy for gravitational potential energy on the way up, and trades it back on the way down. A nuclear reactor converts a tiny amount of mass into thermal energy and radiation. A plant converts sunlight into chemical energy stored in sugar molecules. In every case, the forms change completely. The total does not. Energy is nature's balance sheet, always perfectly balanced, always exact, never rounding, never approximating, never off by even the smallest amount. And it works because the laws of physics are timeless, because the equations describing how the universe operates today are the same equations that described it 1 billion years ago, and the same equations that will describe it 1 billion years from now. And this is why saying everything is made of energy misses the point so completely. Matter is made of particles. At a deeper level, as we will see, matter is made of quantum fields, the fundamental fabric of physical reality. Energy is not a competing ingredient. Energy is a property that those particles and fields possess. It is something they have, not something they are. A moving particle has kinetic energy. A compressed spring has elastic potential energy. A hot gas has thermal energy. But the particle is not built out of energy. The spring is not assembled from energy. They are physical things, and energy is a measurable attribute of those physical things. Saying you are made of energy is like saying a song is made of loudness. Loudness is a real, measurable property of a song. It matters. A loud song and a quiet song are genuinely different. But the song is made of sound waves, not of loudness. Loudness describes an attribute of those waves. In the same way, energy describes an attribute of physical systems. It is not the material they are constructed from. It is a number you can calculate about them. A number that happens to remain constant over time because the laws of physics themselves are unchanging. So far, we have established that energy is not a substance. It is a conserved, measurable property of physical systems. It describes what systems are doing, their motion, their configuration, their internal arrangements, not what they are materially composed of. And its conservation is rooted in the deepest mathematical structure of reality, the time symmetry of physical law, as proven by Emmy Noether over a century ago. But this raises a question that demands an answer. If energy is a property, what kind of property is it at the smallest scales? When you zoom in past molecules, past atoms, past protons and neutrons, down to the quantum level where the fundamental rules of nature change completely, what does energy look like? Because it turns out that at the quantum level, energy does not just describe systems, it constrains them. It dictates which states a system can occupy and which states are absolutely forbidden. And this discovery, which arrived at the very dawn of the 20th century, did not simply refine our understanding of energy. It shattered the classical picture of nature entirely and replaced it with something no one saw coming. Everything we have explored so far describes energy through the lens of classical physics. A conserved property, a quantity that transforms from one form to another but never vanishes. A number tied to the deepest symmetry in the structure of physical law. All of that remains true. But classical physics carries one buried assumption that nobody questioned for centuries. An assumption so obvious that no one even thought to state it out loud. It assumes energy is continuous. Think about what continuous means in practice. Imagine turning a dimmer switch on a lamp. You can set the brightness to any level you want, all the way up, all the way down, or anywhere in between. There are no gaps, no forbidden settings, no minimum brightness below which the light refuses to work. You can always nudge it by a smaller amount, a little brighter, a little dimmer. Infinitely fine adjustments, with no restrictions on what values are allowed. Classical physics assumed energy worked exactly like that dimmer switch. A vibrating string could vibrate with any amplitude. A moving particle could carry any amount of kinetic energy. A heated object could radiate energy in any quantity and any frequency. The spectrum of possible energies was smooth, gapless, and infinitely divisible. This assumption felt so natural that nobody questioned it for over 2 centuries. Of course, you can always have a little more or a little less energy. Of course, there are no gaps. What else could possibly be true? And then, right at the edge of the 19th century, the universe answered that question. The answer demolished classical physics from the foundations up. The crisis started with something deceptively simple: glowing objects. When you heat a piece of metal to a few hundred degrees, it begins to glow a dull red. Heat it further, and the glow shifts to bright orange, then yellow, then white. At extremely high temperatures, objects glow bluish-white. You have seen this yourself if you have ever watched the coils inside a toaster or stared at the filament of an old incandescent light bulb. The color changes with temperature in a completely predictable way. This is called thermal radiation, and every object above absolute zero emits it. Your own body emits thermal radiation right now, though at your body temperature, that radiation is in the infrared range, invisible to your eyes. In the 1860s, physicists began studying this carefully. They wanted to answer a precise question. If you heat an idealized object, one that absorbs all radiation perfectly and reflects nothing, what is the exact spectrum of light it emits at a given temperature? How much energy comes out at each frequency? This idealized object was called a blackbody, not because it appears black when hot, but because it absorbs all incoming radiation without reflecting any. Blackbody radiation turned out to be universal. The spectrum depended only on temperature, not on the material, the shape, the size, or anything else about the object. A blackbody made of iron at 1,000 degrees emitted exactly the same spectrum as one made of carbon at the same temperature. This universality was deeply attractive to physicists. Finding the mathematical formula that correctly predicted the blackbody spectrum became one of the central goals of theoretical physics in the late 1800s. Experimentalists measured the spectrum with extraordinary precision. They could tell you exactly how much energy a black body at a given temperature emitted at every wavelength. The data was clean, detailed, and unambiguous. The challenge was for theorists to derive that spectrum from the known laws of physics, and they failed, catastrophically. The problem was this: classical physics, specifically the combination of Maxwell's electromagnetic theory and the statistical mechanics developed by Ludwig Boltzmann, made a definite prediction for the blackbody spectrum. The calculation assumed that the electromagnetic oscillators in the walls of the blackbody could have any energy, continuous and unrestricted, just like that dimmer switch. Each oscillator could vibrate at any amplitude, and every oscillator at every frequency received its fair share of energy according to the classical laws of thermodynamics. At long wavelengths and low frequencies, the classical prediction matched the experimental data beautifully. But at shorter wavelengths, at higher frequencies, the prediction went horribly wrong. According to the classical calculation, the amount of energy emitted should increase without limit as you move to shorter and shorter wavelengths. It should grow and keep growing, racing toward infinity at the ultraviolet end of the spectrum and beyond. This was nonsensical. It predicted that every object at any temperature above absolute zero should radiate infinite energy at short wavelengths. Your body should be emitting lethal doses of ultraviolet radiation right now. A warm cup of coffee should be flooding the room with gamma rays. Obviously, this does not happen. The real spectrum rises to a peak at some frequency determined by the temperature, and then falls off smoothly at higher frequencies. Hot objects emit plenty of radiation, but the energy per frequency does not climb to infinity. Lord Rayleigh and James Jeans formalized this classical prediction in a formula now known as the Rayleigh-Jeans law. It worked perfectly at long wavelengths, but diverged to infinity at short wavelengths. This spectacular failure was given a dramatic name: the ultraviolet catastrophe. Not a small discrepancy, a complete breakdown. Classical physics, applied rigorously and honestly to a straightforward physical problem, produced an answer that was infinitely wrong. Something fundamental about the classical assumptions had to be incorrect. This is where Max Planck enters the story, and his solution changed everything we thought we knew about the nature of energy. Planck was a German theoretical physicist, meticulous and conservative by temperament, deeply committed to classical thermodynamics. He was not a revolutionary. He did not set out to overthrow the foundations of physics. He set out to fix one annoying equation that refused to match experimental data. In 1900, Planck tried a mathematical trick. He did not claim it was physically meaningful. He simply wanted to see what would happen if he modified the classical assumptions in the smallest possible way. Instead of allowing the electromagnetic oscillators in the walls of the black body to have any energy continuously, he imposed an artificial restriction. He assumed that each oscillator could only absorb or emit energy in discrete chunks, not in any amount, only in specific, indivisible packets. The size of each packet was proportional to the oscillator's frequency. An oscillator vibrating at a higher frequency could only exchange energy in larger packets. An oscillator vibrating at a lower frequency exchanged energy in smaller packets. The proportionality constant linking energy to frequency was a new number, a number Planck introduced purely to make the mathematics work. He called it the elementary quantum of action. Today we call it Planck's constant. Its value is extraordinarily small, about 6.63 times 10 to the negative 34 joule-seconds. This is a tiny number, which is why quantum effects are invisible in everyday life. The packets of energy are so small at ordinary frequencies that they appear continuous, just as a beach appears smooth, even though it is made of discrete grains of sand. From a distance, the graininess vanishes, but it is there. With this single modification, this one restriction on what energies are allowed, Planck derived a formula for the black-body spectrum that matched the experimental data perfectly. At every frequency, at every temperature. The agreement was flawless. His formula, now called the Planck radiation law, reproduced the observed spectrum exactly, including the smooth drop-off at high frequencies that classical physics could not explain. The reason Planck's trick worked was subtle but profound. At high frequencies, where the ultraviolet catastrophe had struck, each energy packet was large because packet size is proportional to frequency. High frequency means big packets, and big packets are hard to produce. An oscillator needs a large amount of thermal energy to emit even a single packet at high frequency. Most oscillators simply do not have enough energy to emit at those frequencies, so high-frequency radiation is suppressed. The energy output falls off at short wavelengths, exactly as observed. The ultraviolet catastrophe was killed by the graininess of energy. Because energy cannot be divided into arbitrarily small amounts at a given frequency, high-frequency modes are effectively frozen out. At low frequencies, the packets are tiny, so small that many of them are available even at modest temperatures. The behavior looks essentially continuous, which is why classical physics worked fine there. The Rayleigh-Jeans law was a low-frequency approximation of the true quantum result. It worked where quantum effects were negligible and failed where they mattered. Planck himself was deeply uncomfortable with his own result. He spent years trying to find a way to derive the correct formula without quantization. He considered the discrete energy packets a calculational trick rather than physical reality, and spent years searching for a deeper classical explanation. He never found one. What happened next was even more disturbing to classical physics. In 1905, the same year he published his work on special relativity, Albert Einstein took Planck's idea and pushed it further than Planck ever intended. Einstein proposed that quantization was not just a mathematical trick for oscillators in a black-body wall. It was a fundamental property of light itself. Einstein was responding to a puzzle called the photoelectric effect, discovered experimentally by Heinrich Hertz in 1887 and studied in detail by Philipp Lenard around 1902. The phenomenon was straightforward. When you shine light on certain metals, electrons are ejected from the metal surface. This was known and well documented. But the details of how the electrons behaved did not match what classical physics predicted. According to classical wave theory, light is a continuous wave. A brighter light carries more energy. So if you shine a dim light on a metal surface, you should just wait. The wave delivers energy gradually, and eventually enough energy accumulates to kick an electron free. A brighter light should deliver energy faster, ejecting electrons sooner and with greater speed. The frequency of the light, whether it is red or blue or ultraviolet, should not matter fundamentally. Any frequency should work if you wait long enough, or make the light bright enough. Every one of those classical predictions was wrong. Experimentally, the photoelectric effect behaved in ways that classical wave theory could not explain. First, there was a threshold frequency. Below a certain frequency, no electrons were ejected no matter how bright the light was. You could blast a metal surface with an incredibly intense beam of red light for hours or years, and not a single electron would come loose. But switch to ultraviolet light, even at very low intensity, and electrons would fly out immediately. Second, when electrons were ejected, their kinetic energy depended only on the frequency of the incoming light, not on its brightness. Higher frequency light produced faster electrons. Lower frequency light produced slower ones. Making the light brighter increased the number of electrons ejected, but each individual electron had the same energy regardless of brightness. Third, the effect was instantaneous. The moment sufficiently high-frequency light hit the surface, electrons came out. There was no delay while energy accumulated gradually, as wave theory demanded. Even with extremely dim, high-frequency light, electrons appeared immediately. Einstein explained all of this with a single radical proposal. Light does not deliver energy continuously, like a smooth wave washing onto a beach. Light delivers energy in discrete packets, individual, indivisible bundles. Einstein called them light quanta. We now call them photons. Each photon carries a specific amount of energy, determined entirely by its frequency. The energy of a single photon equals Planck's constant times the frequency of the light. A photon of red light has low energy because red light has a low frequency. A photon of ultraviolet light has high energy because ultraviolet light has a high frequency. When a photon strikes an electron in a metal, it delivers all of its energy at once in a single interaction. If that energy exceeds the binding force holding the electron in the metal, the electron escapes. If it does not, the electron stays put. No amount of additional red photons will help because each individual red photon lacks the energy to free a single electron. More red photons means more low-energy impacts, not one high-energy impact. It is like trying to knock down a concrete wall by throwing tennis balls at it. Throwing more tennis balls will never work if each one is too soft to do damage. But a single bowling ball might shatter it on contact. This revealed something fundamental. The brightness of light reflected the number of photons it contained. The color of light reflected the energy of each individual photon. These were completely independent properties. You could have many low-energy photons, bright red light, or a few high-energy photons, dim ultraviolet light. Brightness and photon energy were entirely decoupled. Einstein's explanation won him the Nobel Prize in Physics in 1921. Not relativity, which most people assume earned him the prize, but the photoelectric effect. This shows how profoundly important the physics community considered the quantum understanding of light and energy. And Einstein's proposal did something Planck's work had not. Planck quantized the behavior of oscillators in a black-body wall. Einstein quantized light itself. The quantization was not a property of the emitting material, it was a property of the radiation. Energy was fundamentally granular. A few years later, a young Danish physicist named Niels Bohr applied quantization to the atom, and the results were stunning. By 1913, physicists knew that atoms consisted of a dense, positively charged nucleus surrounded by negatively charged electrons. But there was a serious problem. According to classical electromagnetic theory, an electron orbiting a nucleus should continuously radiate energy because it is an accelerating charge, and accelerating charges radiate. As it radiates, it should lose energy, spiral inward, and crash into the nucleus in a fraction of a second. Every atom in the universe should be unstable. Matter itself should collapse almost instantly. Obviously, atoms do not collapse. Matter exists. You exist. Something was deeply wrong with the classical picture. Bohr proposed a radical solution. He declared that electrons in atoms cannot orbit at just any distance with just any energy. They are restricted to specific, discrete orbits. Each orbit corresponds to a specific energy level. An electron in a particular orbit has a particular energy, and that is the only energy it can have while in that orbit. The electron cannot gradually lose energy and spiral inward. That is simply forbidden. It cannot exist between the allowed orbits. There is no in-between. Instead, an electron can only change energy by jumping from one allowed orbit to another. When it jumps from a higher energy orbit to a lower one, it emits a photon whose energy equals exactly the difference between the two levels. Not approximately, exactly. The atom emits a photon with a precise frequency because the energy gap between levels is fixed, and the photon's energy must match that gap perfectly. This explains something that had puzzled scientists for decades. When you heat a gas or pass electricity through it, the gas glows. But unlike a heated solid, it does not glow with all colors equally. Instead, it emits light at only specific, discrete wavelengths. Hydrogen emits red, blue-green, violet, and a few other specific colors with darkness in between. Each element has its own unique set of spectral lines, a fingerprint of characteristic wavelengths. These lines had been meticulously measured and catalogued, but nobody could explain why atoms emitted only those specific colors. Bohr's model provided the explanation. Each spectral line corresponds to an electron jumping between two specific energy levels. The red line in hydrogen's spectrum comes from electrons dropping from the third energy level to the second. The blue-green line comes from electrons dropping from the fourth level to the second. Each jump produces a photon with a specific energy and therefore a specific frequency and color. The pattern of spectral lines is a direct map of the allowed energy levels inside the atom. When Bohr calculated the energy levels for hydrogen using his quantization rules and compared the predicted spectral lines to experimentally measured values, the agreement was extraordinary. He reproduced the known spectral series, the Balmer series, the Lyman series, and others with remarkable accuracy. Quantized energy levels were not just a hypothesis. They produced precise, testable predictions that matched the real world. Over the next decade, the quantum revolution accelerated. In 1925 and 1926, Werner Heisenberg, Erwin Schrödinger, and others developed the full mathematical framework of quantum mechanics. Bohr's simple model of circular orbits was replaced by a far more sophisticated picture involving wave functions, probability amplitudes, and mathematical operators. But the central insight survived and deepened. Energy in quantum systems is not continuous. It is quantized. Physical systems can only occupy specific allowed energy states with real, fundamental gaps between them. In the full quantum mechanical picture, an electron in an atom does not orbit the nucleus like a planet orbiting a star. It exists as a wave function, a mathematical object encoding the probability of finding the electron at any location around the nucleus. Solving the Schrödinger equation for an electron bound to a nucleus produces a set of allowed solutions, like the set of possible notes a particular guitar string can play. Each solution corresponds to a specific energy. Only those energies are permitted. The electron literally cannot have an energy between two allowed levels. It is not that the electron chooses not to. It is that the mathematics of quantum mechanics provides no valid solution at those intermediate energies. The universe simply does not offer those states. But why? What makes only certain energies allowed while all others are forbidden? The answer has to do with the wave nature of quantum particles and a concept you can actually visualize: standing waves. Think about a guitar string. When you pluck it, it vibrates, but it cannot vibrate in just any pattern. Both ends of the string are fixed, they cannot move. This means the vibrations must fit the string's length in a very specific way. The simplest vibration is a single arc, one smooth curve from one end to the other. That is the fundamental note. The next allowed vibration has two arcs, with a motionless point in the middle. Then 3 arcs, then 4. Each pattern fits a whole number of half wavelengths between the fixed ends. You can have 1 half wavelength, 2 half wavelengths, 10 half wavelengths. But you cannot have 2 1/3 half wavelengths. That pattern does not connect smoothly to the fixed endpoints. It would require the string to be in 2 places at once at the boundary. The mathematics forbids it. Only whole number patterns produce stable, self-consistent vibrations. Everything else cancels itself out and vanishes. Electrons in atoms obey a strikingly similar rule. The electron's wave function wraps around the nucleus in 3 dimensions. To be physically valid, the wave function must connect back to itself smoothly after going all the way around. It must be single-valued and continuous at every point. If it does not match up, if the wave would need to have two different values at the same location, the solution is mathematically impossible. Only wave functions that fit whole numbers of wavelengths around the nucleus are permitted. Each valid wave function corresponds to a specific energy, and because only certain wavelengths fit, only certain energies are allowed. The gaps between energy levels are not imposed from outside. They arise naturally from the requirement that the wave function must be self-consistent everywhere. The quantization comes from geometry and boundary conditions, not from energy being made of indivisible pellets. Now, here is the crucial point. The point most people miss, and the point that matters most for understanding what energy is. When we say energy is quantized, it is tempting to imagine that energy comes in little chunks. Tiny pellets of energy stuff, like marbles in a bag. You might picture atoms containing a certain number of energy marbles, and when an atom emits a photon, it is tossing out one marble. This image is appealing, intuitive, and completely wrong. Quantization does not mean energy is made of little pieces of material. It means that physical systems are only allowed to exist in certain states, and each of those states has a specific energy value. The restriction is on the system, not on the energy itself. Energy remains a measurable property. It still describes what a system is doing. It was not a substance before quantization, and it does not become a substance after quantization. What changes is that the property can only take specific values rather than any value on a continuous spectrum. Think of a staircase. You can stand on the first step, the second step, the third step, and so on. You cannot stand between steps. There is no surface to support you there. The allowed positions are discrete and specific, but the discreteness is a property of the staircase, not a property of you. You are not made of stair stuff. You are a person. The staircase constrains where you can stand. Quantum energy levels are the staircase. The physical system, the atom, the molecule, the vibrating field, is the person. The system can only exist at certain energy levels, just as you can only stand on certain steps. But the energy levels are properties of the system's allowed quantum states, not material ingredients composing the system. An atom does not contain energy pellets. An atom exists in a quantum state, and that state has a specific energy value. Transition to a different state, and the energy changes by a specific, fixed amount. The change is discrete because the states are discrete, but the energy remains a property, not a substance. And this brings us to photons, because photons are where the confusion between energy as a property and energy as a substance becomes most acute. People often describe a photon as a packet of energy, a little bundle of energy traveling through space. This description is common even in physics textbooks, and it is deeply misleading because it implies that a photon is a container and that energy is the substance inside the container. A photon is not a container carrying energy the way a truck carries cargo. A photon is a quantum excitation of the electromagnetic field. It is a specific, discrete disturbance in the field, and the energy of that disturbance is determined entirely by its frequency. Higher frequency, higher energy. Lower frequency, lower energy. The relationship is exact and unbreakable. You cannot change a photon's energy without changing its frequency. You cannot have a photon at a certain frequency that somehow carries a different amount of energy. The frequency defines the energy. They are two descriptions of the same physical fact. When an atom emits a photon, it is not ejecting a lump of energy substance from its interior. The atom transitions from a higher energy quantum state to a lower energy quantum state, and the difference in energy between those two states manifests as a new quantum excitation of the electromagnetic field. That excitation is the photon. Its frequency corresponds precisely to the energy difference between the two atomic states. The photon does not exist before the transition. It is not hiding inside the atom waiting to be released. It is created in the act of the transition itself. Before the transition, there is an excited atom and no photon. After the transition, there is a lower energy atom and one photon. The total energy of the combined system, atom plus electromagnetic field, remains exactly the same. Nothing was created or destroyed in a material sense. A property of one part of the system decreased, and a property of another part of the system increased by the same amount. This is important enough to say twice, because it contradicts almost everything popular culture teaches about energy and light. A photon is not a container full of energy. A photon is a quantum excitation whose energy is entirely and inseparably defined by its frequency. You cannot open the photon and pour the energy out. There is no energy separate from the photon. The photon's existence as a disturbance in the electromagnetic field is the energy. If the photon is absorbed by another atom, the excitation vanishes and the atom's energy increases by the corresponding amount. If the photon continues traveling through space, its energy travels with it, because the photon and the energy are not two separate things. They are the same thing described from two angles. This is what quantum physics reveals about energy at the smallest scales. Energy is real. Energy is measurable. Energy comes in specific, quantized amounts when you examine individual quantum systems. But energy remains what it has always been: a property, a description, a number that characterizes the state of a physical system. Quantization did not turn energy into a substance. It revealed that nature is far pickier than anyone imagined about which values that property can take. Classical physics imagined a universe where any energy value was available, a smooth continuum of possibilities. Quantum physics revealed a universe with rules, a universe where only certain values are permitted and all others are absolutely forbidden. Not approximately forbidden, not difficult to achieve, impossible. The states simply do not exist. But if energy is always a property of physical systems, then we need to understand what those physical systems actually are at the deepest level. Because quantum physics did not just quantize energy, it revealed something even more fundamental. It revealed that the universe is not built from particles in the way most people imagine. The universe is built from fields, invisible, space-filling quantum fields that permeate every point in existence. And those fields are where energy truly resides, not as a fluid stored inside them, but as a measurable feature of their behavior. Understanding what fields are and how they carry energy brings us to the deepest layer of the answer. We have established two critical facts about energy so far. First, energy is not a substance. It is a conserved, measurable property of physical systems. Second, at the quantum level, energy is quantized. Physical systems can only occupy specific allowed energy states, with forbidden gaps in between. Both of these insights are essential. But neither of them answers the most natural follow-up question. If energy is always a property of something, then what is that something? What are the physical systems that energy belongs to at the deepest level? What is the universe actually made of, underneath everything? The answer might surprise you. Because the universe is not built from particles. Not really. Not at the most fundamental level. The universe is built from fields. That word, fields, might sound abstract. It might sound like a mathematical formality, a concept physicists invented to make their equations tidier. But fields are not abstractions. They are the most real things in physics. They are the fabric of the physical universe itself. Every particle you have ever heard of, every electron, every quark, every photon, every neutrino, is a localized vibration in an underlying quantum field. And those quantum fields are where energy truly lives. Not as a substance stored inside them, but as a measurable property of their behavior. Understanding fields is the key to understanding what energy actually is at the deepest level physics can currently describe. So what is a field? Let me build the idea from the ground up. Imagine a calm lake on a windless day. The surface of the water is flat and still. Now drop a stone into it. A ripple expands outward. That ripple is not a separate object that was hiding inside the stone. It is a disturbance in the water. The water was already there, covering the entire surface of the lake. The ripple is something the water does, not a new thing added to the water. When the ripple passes a particular point on the lake, the water at that point moves up and down. It carries energy. The ripple transports energy across the lake's surface. But the energy does not travel as an independent substance separate from the water. It travels as a pattern of motion in the water itself. A field in physics is something like that lake, except instead of covering a lake's surface, it fills all of space. Every point in the universe, right now, sits inside multiple overlapping quantum fields. There is an electron field that permeates all of space. There is a quark field. There is an electromagnetic field. There is a Higgs field. There are fields for every type of fundamental particle. These fields exist everywhere, at every point, extending in all directions without boundaries. They are always present, even in the emptiest regions of intergalactic space, even in the hardest vacuum you could ever create. Most of the time, in most places, these fields are in their lowest energy state. They are calm, like the surface of the lake before the stone drops. Nothing dramatic is happening. No particles are present. But the fields are still there. They never vanish. They never switch off. When one of these fields gets excited, when energy is added to it in a specific way, the excitation manifests as what we observe and measure as a particle. An excitation in the electron field is what we call an electron. An excitation in the electromagnetic field is what we call a photon. An excitation in one of the quark fields is a quark. Every particle in the standard model of physics is a ripple, a localized vibration, in its corresponding quantum field. The particle is not a separate object sitting inside the field. The particle is a specific behavior of the field. It is something the field does, just as a ripple is something the lake does. This idea did not appear overnight. It developed over more than a century through the work of many physicists, starting with insights that originally seemed to have nothing to do with fundamental particles. Michael Faraday, working in the 1820s and 1830s, introduced the concept of a field to explain electrical and magnetic phenomena. Before Faraday, the prevailing view was that electric charges and magnets exerted forces on each other across empty space, instantaneously, with nothing in between. This was called action at a distance. A magnet pulls on a piece of iron, even though nothing visible connects them. Nobody had a satisfying answer. The force just seemed to reach through the void. Faraday proposed something different. He suggested that a charged particle creates something real in the space around it. Not a substance you can bottle, but a physical condition of space itself. He called it a field. The electric charge modifies the space around it, and another charge placed in that modified space responds to the local condition of the field, not directly to the distant charge. The interaction is local. The charge at point A creates a field. The field exists everywhere. The charge at point B feels the field at its own location. There is no mysterious action at a distance. There is a field mediating the interaction. Faraday's field concept was initially dismissed by many mathematical physicists who preferred the clean precision of action-at-a-distance formulas. But James Clerk Maxwell took Faraday's intuitive field concept and gave it rigorous mathematical form. In 1865, Maxwell published a unified theory of electricity and magnetism. His equations, now called Maxwell's equations, described electric and magnetic fields as interrelated, dynamic entities that could propagate through space as waves. The speed of those waves, which fell directly out of the equations without being inserted by hand, matched the measured speed of light. Maxwell had discovered that light is an electromagnetic wave, a self-propagating disturbance in the electromagnetic field. And here is where energy enters the picture in a direct, physical way. Maxwell's equations showed that electromagnetic waves carry energy. When sunlight crosses 93 million miles of empty space and warms your face, energy is being transported. But what is carrying that energy? There is nothing between the sun and the earth except vacuum. No air, no water, no physical medium in the ordinary sense. Yet energy arrives. How? The answer is the electromagnetic field. The field itself carries the energy. The oscillating electric and magnetic components of the wave contain energy at every point along the wave's path. This energy is not a substance riding on top of the wave. It is a property of the wave's configuration. Where the electric field is strong and oscillating intensely, the energy density is high. Where the field is calm, the energy density is low. The energy is distributed throughout the field, associated with the field state at every point. This was a revolutionary realization. Energy could be stored in and transported by a field, not just by material objects. A region of empty space with nothing material in it could still contain energy if a field in that region was in an excited state. The field was not empty, even when the space was materially empty. And this insight, born in the 1860s from Maxwell's work on electromagnetism, turned out to be the foundation for all of modern physics. In the 1920s and beyond, physicists took Faraday's and Maxwell's classical field concept and merged it with quantum mechanics. The result was quantum field theory, arguably the most successful theoretical framework in the history of science. In quantum field theory, every fundamental particle is a quantized excitation of an underlying field. The electromagnetic field is quantized into photons. The electron field is quantized into electrons. Each type of particle corresponds to its own quantum field. Paul Dirac made one of the earliest breakthroughs in 1928, developing a quantum theory of the electron that was consistent with both quantum mechanics and Einstein's special relativity. Dirac's equation predicted the existence of antimatter before it was experimentally discovered. It showed that quantum fields have a richness classical fields lack. They can create and destroy particles. When enough energy is concentrated in a region of the electron field, a new electron can pop into existence along with its antiparticle, a positron. When an electron and a positron meet, they annihilate, and their energy transforms into photons, excitations of the electromagnetic field. The particles are gone, but the energy persists, now carried by a different field. This is energy transformation at its deepest level. It is not a substance being poured from one container to another. It is one field settling into a calmer state, while another field becomes more excited. The total energy across all fields remains exactly the same as conservation demands. But the physical form changes entirely. Where there were once particles of matter, there are now quanta of light. The fields rearranged. The energy, being a property of the total system of fields, stayed constant. By the 1940s, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga had developed quantum electrodynamics, a quantum field theory of the electromagnetic interaction that agreed with experiment to an almost absurd degree of precision. Quantum electrodynamics predicted the magnetic moment of the electron to more than 10 decimal places of accuracy, making it the most precisely tested prediction in all of science. This was a triumph of the field concept. The mathematics of quantum fields produced predictions that matched reality to a degree no other theory had ever achieved. So at the deepest level, physics currently describes the universe is made of quantum fields, and energy is a property of those fields. When a field is in its lowest state, its ground state, it has the minimum energy possible. When the field is excited, when ripples and vibrations appear, the energy increases. Each quantum of excitation, each particle, carries a specific amount of energy, determined by the field's properties and the nature of the excitation. But there is another source of energy hidden in matter that has nothing to do with motion or vibration. An energy source so enormous that its discovery reshaped civilization itself. And it comes from mass. In 1905, Einstein published perhaps the most famous equation in all of science: E equals mc squared. Energy equals mass times the speed of light squared. This equation tells us that mass itself is a form of energy. Not that mass can be converted into energy under special circumstances. Mass is energy. They are the same thing, measured in different units. The speed of light squared is a colossal number, about 90 quadrillion in standard units. This means that even a tiny amount of mass corresponds to an enormous amount of energy. 1 kilogram of matter, any matter, contains about 90 quadrillion joules of energy locked inside its mass. That is roughly the energy released by a 20 megaton nuclear weapon. And that is just 1 kilogram. But what does it mean to say mass is energy? This is not a metaphor. It is a precise physical statement. When you weigh an object, when you measure its resistance to acceleration, you are measuring its energy content. A hot object literally weighs more than an identical cold object because the thermal energy of its vibrating molecules contributes to its total mass. A compressed spring weighs more than a relaxed spring because the elastic potential energy stored in the spring contributes to its mass. The differences are fantastically small, far too small to detect with any scale you could buy, but they are real and measurable in principle. Mass and energy are not merely related. They are different names for the same physical quantity, measured in different units, connected by the conversion factor of light speed squared. This means that a particle sitting perfectly still, not moving, not vibrating, not interacting with anything, still has energy. We call this rest energy. It is the energy associated with the particle's mass. An electron at rest has a rest energy of about 0.511 million electron volts. A proton at rest has a rest energy of about 938.3 million electron volts. These are fixed, intrinsic properties of these particles. They cannot be reduced or eliminated without destroying the particle entirely. The rest energy is part of what it means to be that particle. So where does this mass come from? Why do particles have mass at all? This question leads to one of the most celebrated discoveries in modern physics, the Higgs field. In 1964, several physicists working independently proposed a mechanism that could give mass to fundamental particles. Peter Higgs, François Englert, and Robert Brout were among the key contributors. They proposed that there exists another quantum field, now called the Higgs field, that permeates all of space. Unlike most other fields, the Higgs field has a non-zero value even in its lowest energy state. It is never truly calm in the way other fields can be. Its ground state is not zero. It has a constant, non-zero background value everywhere in the universe. When certain particles move through this ever-present Higgs field, they interact with it. That interaction gives them inertia, which we experience and measure as mass. Different particles interact with the Higgs field with different strengths. Particles that interact strongly, like the top quark, are very massive. Particles that interact weakly, like the electron, have much less mass. Photons do not interact with the Higgs field at all, which is why photons are massless and always travel at the speed of light. Think of it this way. Imagine walking through a crowded room. If nobody pays attention to you, you can walk straight through easily. You move freely with no resistance. That is like a photon passing through the Higgs field. Now imagine you are a celebrity. Everyone wants to talk to you. Every step you take, people cluster around you, slowing you down, making it harder to change direction or speed up. That resistance, that drag, is analogous to mass. The more strongly a particle interacts with the Higgs field, the more mass it acquires. In 2012, scientists at CERN announced the discovery of the Higgs boson, a quantum excitation of the Higgs field, confirming that this field exists and behaves as predicted. The discovery was the culmination of nearly 5 decades of theoretical and experimental work, and involved thousands of scientists working with the largest and most complex scientific instrument ever built, the Large Hadron Collider. The Higgs field gives particles their rest mass, and rest mass is rest energy. So in a very real sense, the energy locked inside every massive particle in the universe, the energy described by E equals mc squared, exists because of how that particle interacts with the Higgs field. The rest energy of an electron is a consequence of the electron field's coupling to the Higgs field. Remove the Higgs field from the universe, and electrons would become massless and zip around at light speed like photons. The entire structure of matter, atoms, molecules, planets, people, depends on the Higgs field giving particles the mass that allows them to slow down, bind together, and build complex structures. But here is something that makes this picture even more remarkable, and it is one of the most stunning facts in all of physics. The Higgs field is not the main source of your mass, not even close. When physicists say the Higgs field gives particles mass, that statement is true for fundamental particles like quarks and electrons. The Higgs mechanism is what gives an electron its mass, and what gives each quark its bare mass. But the bare masses of quarks are tiny. The up quark and the down quark, the two types of quark that make up protons and neutrons, have bare masses of only a few million electron volts each. A proton's total mass is about 938 million electron volts. If you add up the bare masses of the 3 quarks inside a proton, 2 up quarks and 1 down quark, you get roughly 9 or 10 million electron volts. That is about 1% of the proton's actual mass. 1%. 99% of the proton's mass comes from somewhere else entirely. Where does it come from? It comes from energy. Specifically, it comes from the kinetic energy of the quarks whipping around inside the proton at close to the speed of light, and from the potential energy stored in the gluon field that binds those quarks together through the strong nuclear force. The interior of a proton is a violent, churning environment. Quarks are not sitting still. They are racing around in a confined space, constantly exchanging gluons, the carriers of the strong force. Those gluons themselves carry energy and can even momentarily split into quark-antiquark pairs before recombining. The total energy of all this furious internal activity, the motion of the quarks, the tension of the gluon field, the constant creation and annihilation of virtual particles, adds up to the vast majority of the proton's mass. This is E equals mc squared made real in the most literal way possible. The proton's mass is not primarily a gift from the Higgs field. It is primarily the energy of motion and interaction inside the proton, manifesting as mass. When you step on a bathroom scale, almost every bit of weight you register comes from the kinetic and potential energy of quarks and gluons inside your protons and neutrons. The Higgs mechanism accounts for barely 1% of your body mass. The other 99% is energy of motion and field interactions, registered by your scale as weight. And here is why this matters for our central question. That 99% of your mass is energy. Not energy as a substance packed inside the proton, like stuffing in a pillow. Energy as a property of how the quarks and gluons are behaving. Their motion, their interactions, their field configurations. All of it adds up to a measurable property, and that property is what shows up as mass on a scale. You literally weigh what you weigh because of motion and interaction at the subatomic level. Mass is not separate from energy. Mass, in the most concrete, everyday sense, is what energy looks like when quantum fields are confined and churning at extreme speeds inside every atom of your body. But mass energy is only part of the story. There is an even stranger kind of energy hidden in the quantum fields, an energy that exists even when nothing is there at all. When physicists say empty space, they mean a region with no particles, no radiation, no excitations of any field, just vacuum. In classical physics, a vacuum is truly empty. No energy, no activity, just blank, inert void. Quantum field theory tells a very different story. Even in a perfect vacuum, the quantum fields cannot be perfectly still. The Heisenberg uncertainty principle, which we encountered earlier, forbids it. You cannot simultaneously know a field's value and its rate of change with perfect precision. This means the fields are always fluctuating slightly, even in their ground state. Tiny, random vibrations ripple through every quantum field at every point in space at all times. These are called quantum fluctuations, or vacuum fluctuations. These fluctuations carry energy. Even empty space, the most perfect vacuum imaginable, has energy. This is called vacuum energy, or zero-point energy. It is not zero. It is the minimum energy the quantum fields can have. And that minimum is greater than zero because the uncertainty principle prevents the fields from ever being perfectly still. This is not speculation. We have measured the effects of vacuum energy directly. The Casimir effect, first predicted in 1948 and subsequently confirmed experimentally, demonstrates vacuum energy in a beautifully simple way. Take two uncharged metallic plates and place them very close together in a vacuum, separated by only a tiny gap. Classical physics predicts nothing should happen. There are no charges, no currents, no forces. But quantum field theory predicts the plates will be pushed together by a measurable force. The reason is vacuum fluctuations. Between the plates, only certain wavelengths of fluctuation can fit. The plates act like walls, constraining which vibrations are possible in the gap. Outside the plates, all wavelengths are allowed. There are more possible fluctuations outside the plates than between them. The imbalance creates a net pressure pushing the plates together. This pressure has been measured, and it matches the theoretical prediction. The vacuum, apparently empty space with nothing in it, exerts a real, physical, measurable force on material objects. This confirms that the quantum vacuum is not empty. It seethes with energy. The fields are always fluctuating, always vibrating at their minimum level, and those fluctuations carry real energy with real physical consequences. But here is the critical point. The vacuum energy is not a substance filling space like an invisible gas. It is a property of the quantum fields in their ground state. The fields exist everywhere. In their lowest energy configuration, they still fluctuate, and those fluctuations have an associated energy. The energy belongs to the fields. It is an attribute of how the fields behave, even when they are as calm as quantum mechanics allows them to be. Now let us step back and look at the complete picture of how energy exists in and moves through physical systems, because the field perspective unifies everything we have discussed. Energy moves through the universe in several ways, and every single one of them involves fields. Radiation is the most obvious example. When the sun emits light, excitations in the electromagnetic field, photons, travel outward through space. Each photon carries energy proportional to its frequency. When a photon strikes your skin, it is absorbed. The excitation in the electromagnetic field vanishes, and the energy transfers to the electron field in the atoms of your skin, increasing the kinetic energy of those electrons and the thermal energy of your tissue. You feel warmth. Energy has moved from the sun to your body, transported entirely by fields. Conduction works through fields as well, though less obviously. When you touch a hot stove, thermal energy transfers from the stove to your hand. At the atomic level, the more energetic atoms in the stove are vibrating rapidly. Their electrons and nuclei are oscillating in their quantum states. When your skin contacts the stove, the rapidly vibrating atoms of the stove interact with the slower atoms of your skin through electromagnetic forces, through the electromagnetic field. The fast atoms transfer kinetic energy to the slow atoms, exciting them to higher energy states. Heat flows from hot to cold, mediated entirely by electromagnetic field interactions between neighboring atoms. Chemical reactions are field rearrangements. When you burn wood, you are rearranging the electron configurations of carbon and oxygen atoms. The electrons in the wood's molecules are in certain quantum states with certain energies. After combustion, those electrons occupy different quantum states in carbon dioxide and water molecules, and those new states have lower total energy. The difference is released as thermal energy and light. Excitations in the electromagnetic field carry the light. The increased jiggling of product molecules carries the heat. Every step is a field process. The electron field reconfigures. The electromagnetic field carries away the excess energy. Nothing mysterious flows from one place to another. Properties of fields change, and those changes propagate. Nuclear reactions work the same way at a deeper level. In nuclear fission, a heavy nucleus splits into lighter fragments. The total mass of the fragments is slightly less than the mass of the original nucleus. That missing mass has been converted into kinetic energy of the fragments and energy of emitted radiation, exactly as E equals mc squared predicts. But what is actually happening at the field level is that the quark and gluon fields inside the nucleus have rearranged into a lower energy configuration. The strong nuclear field, which binds quarks into protons and neutrons, releases energy as the nuclear geometry changes. The fields settle into a state with less mass, and the energy difference appears as motion and radiation. Even gravity involves energy in fields, though the details are more subtle and not fully resolved by current physics. In general relativity, the gravitational field, which is the curvature of space-time itself, carries energy. Gravitational waves, ripples in the fabric of space-time first detected in 2015, transport energy across the cosmos. When two black holes spiral into each other and merge, they radiate enormous amounts of energy as gravitational waves. That energy was stored in the gravitational field configuration of the binary system, in the curvature of space-time around two massive objects orbiting each other. As the objects merge, the field configuration changes, and energy radiates outward as ripples in space-time. In every case, without exception, energy is a property of fields and their configurations. When energy transfers from one system to another, what actually happens is that one field's excitation decreases and another field's excitation increases. When energy transforms from one form to another, fields rearrange. Chemical energy becoming thermal energy is electron fields reconfiguring and electromagnetic fields carrying away the difference. Mass becoming radiation is matter fields de-exciting and photon fields exciting. Gravitational potential energy becoming kinetic energy is space-time curvature changing as objects fall, with the field configuration evolving according to the equations governing it. Energy never exists independently of fields. You cannot have energy floating on its own in empty space, separate from all physical systems. If there is energy somewhere, there is a field there, and that field is in a state that corresponds to that energy value. Energy is always the energy of something. It is a measurable feature of a physical system. It belongs to fields, to particles which are themselves field excitations, to configurations of matter and radiation. Strip away all the fields and there is nothing left. No space, no time, no matter, no radiation, and no energy. Energy does not survive the removal of all physical systems because energy is not an independent entity. It is a description of how physical systems behave. This understanding also clarifies a common source of confusion about the phrase pure energy. You hear it in science fiction constantly. A weapon converts matter into pure energy. An advanced civilization exists as beings of pure energy. The idea suggests that energy can exist in some raw, unattached, refined form, separate from matter, separate from fields, floating freely as a kind of ultimate substance. Physics offers no support for this idea. There is no such thing as pure energy. Energy without a physical system to belong to is meaningless. When matter and antimatter annihilate, the energy does not become free-floating pure energy. It becomes photons, which are excitations of the electromagnetic field. The energy went from being carried by the electron field and the positron field to being carried by the electromagnetic field. It changed which field carried it, but it never stopped belonging to a field. It was never unattached. It was never pure in the sense of being liberated from physical reality. It was always the energy of some specific physical system. Even the vacuum energy we discussed earlier belongs to the quantum fields. It is the energy of the fields in their ground state. Remove the fields, which you cannot actually do because the fields are the foundation of physical reality, and the vacuum energy would vanish too. It is not independent. It is a property of the fields that fill space. So the picture that emerges from quantum field theory is coherent and deep. The universe is made of quantum fields. Particles are excitations of those fields. Energy is a measurable property of fields and their excitations. Energy can be transferred from one field to another. Energy can change form as fields rearrange. But energy never exists on its own, separate from all fields and all physical systems. It is always the energy of something. And that something, at the deepest level we currently understand, is always a quantum field. This is the foundation on which the final answer rests. We have traced energy from its everyday misidentification as a substance through the classical discovery that it is a conserved property, through the quantum revolution that revealed it comes in discrete amounts, and now through the field-theoretic understanding that it belongs to the quantum fields permeating all of reality. What remains is to bring these threads together into a single clear statement of what energy actually is according to quantum physics, and to confront directly why the popular picture of energy as a substance, as stuff, as the material from which reality is built, is not just imprecise, but genuinely misleading. We have travelled a long road to get here. We started with the everyday intuition that energy is a substance, an invisible material hidden inside objects waiting to be released. We watched that intuition collapse under the weight of history, as the parallel story of caloric theory showed us how confidently science can be wrong about the nature of a phenomenon it can perfectly well measure. We followed energy through the classical revolution, where it was revealed to be a conserved property of physical systems, its conservation guaranteed not by any material indestructibility, but by the time symmetry of nature's laws, as proven by Emmy Noether in 1918. We descended into the quantum world, where energy turned out to be quantized, restricted to specific allowed values, not because energy itself comes in little pieces of stuff, but because physical systems can only exist in certain quantum states. And we explored the field-theoretic foundation, where the universe is built from quantum fields permeating all of space, with particles as excitations of those fields and energy as a measurable property of how those fields behave. Now it is time to put the answer into plain language. What is energy actually made of according to quantum physics? It is not made of anything. Energy has no ingredients. It has no internal composition. It is not assembled from smaller components. You cannot break energy apart and find what it contains, because it does not contain anything. Energy is not a substance, not a material, not a fluid, not a particle, not a field. Energy is a property, a measurable, quantifiable, conserved property of physical systems. I know that answer might feel unsatisfying at first. We asked what energy is made of, and the answer is that the question itself is built on a false assumption. It assumes energy is the kind of thing that can be made of something, but not everything that is real is made of stuff. Some real things are properties rather than substances. Temperature is real, but it is not made of anything. Speed is real, but it is not made of anything. Angular momentum is real, but you cannot put it under a microscope and examine its composition. These are measurable attributes of physical systems. They describe what systems are doing. They are not substances lurking inside systems alongside the material that composes them. Energy belongs to this category. It is a number you can assign to any physical system based on the system's state, configuration, motion, and internal structure. That number obeys strict rules. It is conserved in every physical process. It can change form, shifting between kinetic energy, potential energy, thermal energy, mass energy, radiation, and other manifestations. But the total always remains the same. Energy is nature's most meticulous bookkeeping entry, an accounting quantity that the universe tracks with absolute precision across every interaction, every transformation, every event that has ever occurred or ever will. But let me be careful here, because there is a way to misunderstand what I am saying that would be just as wrong as the substance picture. When I say energy is a property, I do not mean it is unreal. I do not mean it is merely a human invention, a convenient fiction we impose on the universe to make calculations easier. Energy is objective. It is measurable. It has physical consequences that you can observe and feel. A truck moving at 60 miles per hour has a certain kinetic energy, and if it hits a wall, that energy transforms into deformation, heat, and sound in ways that are absolutely real and absolutely determined by the amount of energy involved. Energy is not a social construct. It is not a metaphor. It is a real, objective feature of the physical world. It is just not a substance. It is a feature of the same category as shape or motion, not of the category of matter or material. This distinction between a real property and a substance is the core of the answer, and it is the distinction that almost everyone, including many science communicators and popular science writers, consistently blurs. Consider the phrase that probably brought you here tonight. Everything is made of energy. You hear it in documentaries. You read it in books about quantum physics written for general audiences. You see it in online discussions about the nature of reality. Sometimes it is presented as a profound insight from modern physics, a revelation that matter is an illusion and energy is the true fundamental reality. The implication is that if you could zoom in far enough, past molecules, past atoms, past quarks and electrons, you would eventually find pure energy at the bottom. The ultimate building block, the primordial stuff from which all things are assembled. This is wrong, and it is worth being very specific about why, because the error is not a minor quibble. It leads to genuine confusion about how the universe works, and it opens the door to pseudo-scientific claims that exploit the confusion. Matter is not made of energy. Matter is made of quantum fields. Specifically, matter is made of excitations in fermionic quantum fields, the electron field, the quark fields, the neutrino fields. These excitations are what we observe and measure as particles. The particles have energy. They have mass, which is itself a form of energy. They have kinetic energy if they are moving. They have potential energy if they are in a configuration where forces could cause them to move. But the energy is a property of the particles, not the material the particles are made from. Saying matter is made of energy is like saying a hurricane is made of speed. A hurricane has speed. Speed is one of the most important properties of a hurricane. The speed of its winds determines how destructive it is, what category it falls into, how much damage it will do. But the hurricane is made of air and water, not of speed. Speed describes what the air and water are doing. It is not the substance they are composed of. Or consider a different analogy. A symphony has volume, pitch, rhythm, and harmony. These are real, measurable properties of the symphony. They determine what the symphony sounds like, how it affects listeners, whether it is powerful or gentle. But the symphony is made of sound waves, vibrations in air pressure produced by instruments. The symphony is not made of volume. Volume is a property of the sound waves. You cannot extract the volume from a symphony and hold it separately. You cannot have volume without sound waves to carry it. The property depends on the physical substrate. Remove the substrate and the property vanishes. Energy works the same way. Remove all the quantum fields, all the particles, all the physical systems from a region of the universe, and there is no energy left. Not because you cleaned the energy out, but because energy cannot exist without a physical system to belong to. There is no free-floating energy drifting through the void, unattached to any field, any particle, any physical entity. Energy is always the energy of something. It is defined by and inseparable from the physical system whose property it is. This is why the concept of pure energy, so beloved by science fiction, has no basis in physics. We already saw what actually happens when matter and antimatter annihilate. Energy does not escape into some liberated, free-floating state. It simply moves from one field to another without ever being unattached. But the point extends far beyond that single example. Think about what it would even mean for energy to exist on its own. It would be a property without a system, a speed with nothing moving, a temperature with nothing hot. It is not just physically impossible, it is logically incoherent. A property describes something. Without that something, the property is not floating free. It simply does not exist. There is no container you could build, no experiment you could run, no condition you could create that would isolate energy from all physical systems, because energy is defined by those systems. Even in the most extreme environments physics can describe, energy never becomes an independent entity. Inside a black hole, at the moment of the Big Bang, in the most intense particle collisions we can produce, energy always belongs to fields and their configurations. There is no regime, no condition, no extreme where energy peels away from physical systems and exists as a thing in itself. The physics does not allow it. The mathematics does not describe it. It is not a limitation of our current theories that might be overcome by future discoveries. It follows from the fundamental structure of how energy is defined. Energy is a property. Properties do not float free of the things they are properties of. Now let me address why this matters beyond physics. Because the misunderstanding of energy as a substance has real consequences outside the laboratory. The moment people start thinking of energy as a material substance, as an invisible cosmic fluid that flows through all things, they become vulnerable to claims that have no scientific basis. You see this in alternative medicine, where practitioners claim to manipulate your body's energy or rebalance your energy flow. You see it in spiritual movements that describe the universe as fundamentally made of energy and consciousness. You see it in product marketing, where devices claim to emit healing energy or harmonize the energy in your home. None of these claims have any connection to how physics defines and uses the word energy. They borrow the authority of a scientific term while using it to mean something entirely different. The scientific word energy refers to a precisely defined, measurable, conserved quantity in physics. The popular word energy, as used in these contexts, refers to a vague, unmeasurable, undefined substance that has no relationship to the physics concept beyond sharing a name. This is not an innocent confusion. It costs people money and health outcomes when they choose energy healing over medicine. It muddies public understanding of real scientific issues like energy policy and climate change. When the word energy means completely different things to scientists and to the general public, communication breaks down, and people who genuinely want to understand the universe are left with a picture that is actively misleading. Understanding that energy is a property, not a substance, is a form of intellectual self-defense. It gives you the tools to evaluate claims critically. If someone tells you they can manipulate energy with their hands, you can ask, energy of what system? What is the measurable quantity that is changing? How is it being measured? What is the conservation law that governs this process? These are not hostile questions. They are the questions that physics demands you ask about any claim involving energy. And if the answers are vague or non-existent, that tells you the claim is not about energy in the scientific sense, regardless of what vocabulary it uses. Let me now draw together the threads of everything we have explored and lay out the complete picture of energy as quantum physics reveals it. Energy manifests in several forms, and each form corresponds to a specific physical situation involving fields, particles, and their behaviors. Kinetic energy is the energy of motion. A moving particle has kinetic energy proportional to its mass and the square of its velocity. At the quantum level, kinetic energy is associated with the momentum of a particle, which in turn relates to the wavelength of its quantum wave function. Shorter wavelength means higher momentum, means higher kinetic energy. Motion is not a substance, it is something a particle does, and kinetic energy is the number that describes how much of it the particle is doing. Potential energy is the energy of configuration. It describes the energy a system has because of how its parts are arranged relative to the forces acting on them. A rock at the top of a cliff has gravitational potential energy because of its position in the Earth's gravitational field. An electron near a proton has electromagnetic potential energy because of its position in the proton's electric field. Potential energy is not stored inside the rock or the electron as a hidden substance. It is a property of the relationship between the object and the field it sits in. Change the relationship, let the rock fall or the electron move closer to the proton, and the potential energy converts to kinetic energy. The number changes because the configuration changes. Mass energy is the energy associated with a particle's rest mass, described by Einstein's E equals mc squared. This is the energy a particle has simply by existing, even when it is not moving and not interacting with anything. As we saw earlier, most of the mass you experience in daily life does not come from the Higgs mechanism at all. It comes from the furious motion and interaction of quarks and gluons confined inside every proton and neutron. That internal activity is energy, energy of motion and field interaction, and it manifests as the mass your bathroom scale registers. Mass is not separate from energy. It is one specific form of energy, the form associated with a system's existence and internal structure. Radiant energy is the energy carried by electromagnetic radiation, by photons. Each photon's energy is determined by its frequency. A gamma-ray photon carries millions of times more energy than a radio wave photon. This energy travels through space at the speed of light, transported by the electromagnetic field. When a photon is absorbed, its energy transfers to whatever absorbs it, typically an electron in an atom, which jumps to a higher energy state. The energy was never a substance inside the photon. It was a property of the electromagnetic field's excitation. Thermal energy is the collective kinetic energy of enormous numbers of particles jiggling, vibrating, and bouncing around. A hot gas has more thermal energy than a cold gas because its molecules are moving faster on average. Temperature measures the average kinetic energy per particle. Thermal energy is not a substance mixed in with the gas molecules. It is a statistical description of how all those molecules are behaving collectively. Each of these forms is different. They describe different physical situations, different configurations of fields and particles, but they are all the same quantity measured in the same units, governed by the same conservation law. You can convert kinetic energy into thermal energy by slamming on the brakes. You can convert mass energy into radiant energy in a nuclear reaction. You can convert potential energy into kinetic energy by dropping a ball. The forms change, but the total never does. The universe's books remain balanced to the last decimal place. And this conservation, as Noether proved, is not a coincidence. It is a mathematical consequence of time symmetry. Because the laws of physics do not change from one moment to the next. Because the equations governing forces and fields and particles are the same today as they were 1 billion years ago and will be 1 billion years from now, a conserved quantity must exist. That quantity is energy. It is not conserved because it is an indestructible substance. It is conserved because the rules of the game do not change over time. The conservation of energy is a reflection of the universe's temporal consistency. Change the laws of physics over time and energy conservation would break. Keep the laws constant and energy conservation is mathematically guaranteed. This is perhaps the deepest insight of all. Energy is not a thing the universe contains. Energy is a consequence of how the universe behaves. It is a symmetry property, a structural feature of the laws of nature themselves. The universe does not have energy the way a glass has water. The universe obeys rules that are constant in time, and energy is the mathematical quantity that this constancy guarantees will be conserved. Energy emerges from the structure of physical law rather than existing as an ingredient of physical matter. Let me offer one final way to think about this, because I want the picture to be as clear as possible. Imagine you are watching a chess game. The pieces move around the board following strict rules. Knights jump in L-shaped patterns, bishops slide diagonally, rooks move in straight lines. Now imagine someone asks you, what is the material balance of the game made of? You might count up the values of the remaining pieces for each side. A queen is worth 9 points, a rook 5, a bishop 3, and so on. That material balance is real. It matters enormously. A player who is up a queen will almost certainly win. The number has genuine predictive power. You can use it to assess who is winning and by how much. But the material balance is not a substance on the chessboard. It is not a physical thing sitting in a square somewhere, waiting to be captured. It is a number calculated from the configuration of the pieces. Change the configuration, capture a piece, promote a pawn, and the number changes. But at no point does material balance exist as an independent entity. It is always a property of the arrangement of pieces on the board. Remove the pieces and the board, and the material balance ceases to exist, not because you destroyed it, but because it was never a thing in the first place. It was a description, a useful, powerful, consequential description, but a description nonetheless. Energy in physics plays a similar role on a vastly deeper level. It is the universe's material balance, a number calculated from the configuration of fields and particles that has genuine, absolute, predictive power. It determines what transformations are possible and what transformations are forbidden. It constrains the future evolution of every physical system. It governs the structure of atoms, the burning of stars, the chemistry of life, the motion of galaxies. It is arguably the single most important quantity in all of physics. But it is not a substance. It is not a building block. It is not what things are made of. It is a description of what things are doing, governed by laws that are woven into the deepest fabric of space-time. So, the next time you hear someone say, "Everything is made of energy," you will know what they actually mean, and you will know why that phrase, though poetic, misses the truth. Everything is made of quantum fields. Fields that fill all of space. Fields that vibrate and fluctuate and excite into the particles we observe and the forces we feel. Energy is a property those fields possess, a property that transforms, transfers, and converts from one manifestation to another, but always remains exactly conserved, never created, never destroyed, always belonging to something physical, never floating free. Energy is not what the universe is made of. Energy is how the universe keeps track of itself. It is the ledger, not the goods. The score, not the game. The rhythm, not the music. It is real. It is vital. It is inescapable. And it governs everything. But it is not a substance. It never was. And understanding that, truly understanding it, changes how you see every star, every atom, every field, every interaction, every moment of the physical universe we inhabit. You are not made of energy. You are made of quantum fields. Excitations rippling through the electron field, the quark fields, bound together by the electromagnetic field and the strong field, given mass by the Higgs field, held to this planet by the gravitational field. And every one of those fields has energy. Your kinetic energy as you move through the world. Your thermal energy as trillions of molecules vibrate inside you. Your mass energy, that vast reservoir locked in every proton and neutron in your body, enough to power a city for centuries if it could somehow be fully released. Your chemical energy, stored in the molecular bonds that hold your proteins and fats and sugars together. All of that energy is real, all of it is measurable, and all of it is a property of the physical systems that compose you. It describes what your fields and particles are doing at this very moment. It does not describe what you are made of. What you are made of is far more interesting. You are made of the same quantum fields that fill the entire universe, vibrating in patterns complex enough to think, to wonder, to ask what energy is, and to understand the answer. The universe is not a container full of energy. The universe is a system of quantum fields whose behavior is governed by laws that do not change over time. And energy is the name we give to the quantity that this timelessness guarantees will be conserved. It is not the stuff of existence. It is the signature of existence's deepest symmetry. A symmetry so fundamental that without it, physics as we know it could not function. Stars could not burn predictably. Atoms could not hold together reliably. Chemistry could not proceed consistently. life could not sustain itself. Energy is the universe's promise that the rules will not change. And as long as that promise holds, energy will be conserved, transformed endlessly from one form to another, but never created, never destroyed, always accounted for, always balanced, always exact. That is what energy is. Not a substance, not a material, not a building block. A property, a conserved quantity, a reflection of the deepest symmetry in nature. And that, when you truly understand it, is more profound than any glowing cosmic fluid could ever be. Thank you for staying with me through this entire journey. If you found this exploration valuable, a like or subscribe would mean the world. And the next time someone tells you that everything is made of energy, you will know the real answer. Everything is made of quantum fields. Energy is what those fields have, not what they are. And understanding the difference changes everything. Good night, and may you never hear the word energy quite the same way again.